Right, in this video we're going to be looking at the geometric distribution. So this is similar to the binomial distribution, but the difference now lies in that in the binomial distribution we had a fixed number of trials. In the geometric distribution we no longer have a fixed number of trials. In fact, in the geometric distribution we are investigating the number of trials up until our first success. Number of trials up until first success. So the condition for a random variable to be defined geometrically are similar to those of a binomial distribution in that we should have two outcomes, success or failure. So two outcomes are success or failure, and we should have a constant probability of success. P is constant, and our trials should be independent. Trials are independent. Alright, and now the key difference is that for a binomial distribution we had a fixed number of trials, but for a geometric distribution number of trials are not fixed. So number of trials are not fixed. Okay, and if a random variable x satisfies these conditions, we can define it or distribute it geometrically, and we only take one argument or one parameter, which is the probability of success. And if you want to find the mean under a geometric distribution, that's going to be the expectation of x is 1 over p. And we don't find variance for geometric distribution in this syllabus, so don't worry about that. So to evaluate geometric probabilities, we use the formula. The probability that x is equal to r is equal to 1 minus p to the power r minus 1 multiplied by p. And in most literature you find 1 minus p written as q. So that means this formula can also be written as q to the power r minus 1 multiplied by p. So let's look at some questions on the geometric distribution. Here we're given that two fair coins are thrown at the same time. The random variable x is the number of throws of the two coins required to obtain two tails at the same time. Find the probability that the two tails are obtained for the first time on the 7th throw. So this word first is a keyword to tell you that you are under a geometric distribution, because under a geometric distribution all we're looking for is our first success. We're going to keep trying something until we succeed at it once. So we're looking for that first success. So you look for the keywords first and until. So until something happens or until we get our first success. So these will be your keywords. Once you see those keywords, chances are you're dealing with a geometric distribution. Alright, so we've been given that x is the number of throws of the two coins required to obtain two tails at the same time. And we want to find the probability that two tails are obtained for the first time on the 7th throw. So x follows a geometric distribution. We want to obtain two tails. So the probability of obtaining a tail when you throw a single coin is 1 over 2. And so getting two tails when you throw two coins is going to be 1 over 2 times 1 over 2, which is a quarter, which I'll write as a decimal, 0.25. So 0.25. You can give your probability here as a fraction as well. Now we want to find the probability that the two tails are obtained for the first time on the 7th throw. So we want to find the probability that x is equal to 7. So this is equal to 1 minus p, which is q. Q is 1 minus 0.25, so q is 0.75. So 0.75 to the power 7 minus 1, so 6, multiplied by the probability of success, so 0.25. So the probability that x is equal to 7, this is, let's punch that into the calculator, that's 0.75 to the power 6 times 0.25. So that's going to give us 0.0445, and that's our final answer. Part B says find the probability that it takes more than 9 throws to obtain 2 tails for the first time. So more than 9, that means we want the probability that x is greater than 9. So since we don't have a fixed number of trials for a geometric distribution, if we're given greater than 9, we don't know if greater than 9 means 10, 11, 12, 13, 14, 15, or even going up to 20 or beyond 100, because the number of trials are not fixed. So we can't really calculate going forwards. So we will use the idea that this can be written as 1 minus the probability that x is less than or equal to 9, because we can count backwards. We know that less than or equal to 9 is 1 through 9. X can't be 0 on a geometric distribution because remember, this is the number of trials up until a first success. So we cannot have 0 trials up until a first success. You have to try at least once to succeed. I am philosophizing in A-level maths. Yeah. But seriously though, you have to try at least once to succeed in life. But anyways, I digress. The point is, here we have to evaluate the probability that x is equal to 1, x is equal to 2, up until we get to x is 9. So it's going to be using the formula q to the r minus 1 times p. For x is 1, for x is 2, for x is 3, for x is 4, for x is 5, for x is 6, for x is 7, for x is 8, for x is 9. You can see how this can very quickly get tedious. So there is a shorter formula you can use that states that in general, if you've got a probability of the form x is greater than r, your result is going to be q to the power r. So what this means is that in our case, this becomes our q is 0.75, and this is to the power r, so it's going to be to the power 9. So the probability that x is greater than 9 is equal to 0.75 to the power 9. So let's punch that into the calculator and we get 0.0751, and this would be our final answer. So now you're probably wondering, if we've got a shortcut for the greater than sign, do we also have a shortcut for the less than sign? Yes, we do, and it's for less than or equal to r, and that's going to be 1 minus q to the r. So if you want to find the probability that x is less than or equal to r, you use 1 minus q to the r. We've got an example that we'll look at that will require this solution. So let's look at the next example. Here we're given that an ordinary fair die is thrown repeatedly until a 5 is obtained. So that keyword that I mentioned, an ordinary fair die is thrown repeatedly until a 5 is obtained. The number of throws taken is denoted by the random variable x. So we know that our random variable x follows a geometric distribution. And what are we doing? We are trying to obtain a 5 from a fair die. So a fair die has 6 possible outcomes. So the probability of obtaining a 5 is 1 out of 6. So this is 1 out of 6. And part A says write down the mean of x. So recall that mean under a geometric distribution is 1 over p. So this means that our expectation is going to be 1 over 1 over 6. And so if we resolve our fraction, this becomes 6. Okay, so that's part A. Part B says find the probability that a 5 is first obtained after the 3rd throw but before the 8th throw. So after the 3rd throw, probability that x is greater than 3, and before the 8th throw, so less than 8. Alright, so this means we want the probabilities x is 4, x is 5, x is 6, and x is 7. So let's evaluate each probability individually. So we'll start with x is 4. That's going to be q which is 1 minus 1 over 6. Q is 1 minus 1 over 6, so Q is 5 over 6. So 5 over 6 to the power 4 minus 1, so 3 multiplied by the probability of success, 1 over 6. This is for x is 4. Now let's go on to x is 5. X is 5 is going to be, that's 5 over 6 to the power 5 minus 1, so that's 4, multiplied by 1 over 6, plus x is 6, that's going to be 5 over 6 to the power 5, multiplied by 1 over 6. Alright, and then finally we want to go on to x is 7. So that's going to be 5 over 6 to the power 7 minus 1, which is 6, multiplied by 1 over 6. Okay, and so this is the probability that x is equal to 4, 5, 6, or 7. So let's evaluate each individual probability. So we've got 5 over 6 to the power 3 multiplied by 1 over 6, and that gives us 0.0964506 plus, let's go on to x is 5, that's 5 over 6 to the power 4 times 1 over 6, so that gives us 0.0803755 plus, let's go on to 6, that's 5 over 6 to the power 5 multiplied by 1 over 6, and that gives us 0.0669796 plus, let's go on to x is 7, so that's 5 over 6 to the power 6 multiplied by 1 over 6, and that gives us 0.005586163. Alright, so let's add up all our probabilities. This is 4, 5, 6, 7. So that's going to be 0.0964506 plus 0.08033755 plus 0.0669796 plus 0.0558163, and this gives us 0.2996. So to three significant figures, that would be 0.300, and that would be our final answer. Now part C says find the probability that a 5 is first obtained in fewer than 10 throws. So that's the probability that x is less than 10. So that would mean the probability that x is 1, x is 2, all the way up to x is 9. Okay, so obviously this would get very tedious very quickly. So instead of evaluating all of those individual probabilities, we're going to use the idea I mentioned in the previous question. We said for the less than or equal to r, this can be written as 1 minus q to the r. These shortcuts are not in the formula booklet, so you should know them by heart. That's probability that x is greater than r. This one will be q to the r. You should memorize these two formulas. They will save you a lot of time and a lot of headaches with geometric distributions. So since we've got x is less than 10, it resembles this formula, but we need that or equal to part. So to do that, remember that this is discrete, so x is less than 10 is the same as x is less than or equal to 9. So this means this becomes 1 minus q. Our q for this question is 5 over 6. 5 over 6 to the power, that's the power r, so to the power 9. So it means the probability that x is less than or equal to 9 is equal to, let's punch that into the calculator, that's 1 minus 5 over 6 to the power 9. And that gives us 0.806, and that is our final answer. Alright, so that's it for the geometric distribution. Make sure to go through the quiz, and I'll see you in the next video.